Welcome back to today's Explainer. We're doing something really cool today. We are tracing an epic, literal journey of a single photon right across the globe. You see, we're not just talking about some simple data transfer here. No. We're looking at the actual, physical routing mechanics of sending a quantum signal from one side of the planet all the way to the other to deliver completely unhackable data. It's this absolutely fascinating intersection of advanced materials science on the ground and hyper-precise satellite relays up in space. Okay, let's dive into this and check out our flight itinerary so you know exactly where we're heading today. We're going to start with the Quantum Coherence Challenge, launch from Jitterbug Hub A, jump up to the Solstice Node Space Relay, track the descent down into Jitterbug Hub B, and finally wrap up with perfect quantum reconstruction. First up, Section 1, the Quantum Coherence Challenge. So before we actually launch our photon, we've got to face the primary villain of our story here: vast, chaotic physical distance. And to understand exactly why distance is the ultimate enemy, we have to talk about coherence. Right? So coherence is essentially the incredibly fragile act of keeping that delicate quantum state from collapsing over these vast distances. It's the fragile package that our photon hero has to protect at all costs. Because, in a normal environment, a photon just wants to scatter. It naturally wants to lose that quantum information. So our entire routing architecture, from the hubs on the ground to the orbital constellations, exists for one singular purpose: solving this challenge and protecting that delicate state from scattering during its global journey. Moving on to Section 2, launching from Jitterbug Hub A. All right, let's head to the starting line. Deep inside the local Jitterbug Hub A, inside this 5-sided insulated tunnel, there's a staggering stack of material science engineered to create a perfectly clean energy landscape. It's honestly incredible. First, we've got a magnesium, zinc, or MgZn crystal matrix that's precisely doped with rare earth elements, specifically erbium and ytterbium. Right next to that sits a ruby crystal cavity absolutely loaded with chromium ions. And the real kicker? Supporting this entire deck is a maglev drive. It literally physically levitates the system in midair to absolutely 100% eliminate any mechanical jitter that could possibly disturb our photon. So all that brilliant hardware works together in a seamless 3-step launch sequence. In step 1, an initial photon seed gets introduced into that MgZn matrix. And thanks to the erbium and ytterbium, the photon is guided through this beautifully clean energy landscape that minimizes scattering, successfully stamping the initial quantum info right onto the wave packet. Then we hit step 2, cavity gain and photon recycling. The photon passes into the ruby crystal cavity, where those chromium ions narrow the emission line, which really sharpens the signal. But here's the absolute genius part. If any photons try to scatter or escape, the photon recycling mechanics instantly reflect them back into the active path. It's literally like putting the bumpers up in a bowling alley. It perfectly preserves the signal's amplitude without needing massive amounts of external power. And finally, step 3. The stabilized signal is converted to the V-band frequency spectrum. Now, V-band is highly directional, which inherently prevents any side-channel eavesdropping, and it's perfectly optimized to pierce right through our local atmospheric boundary layer, heading straight up toward the nearest overhead satellite. Let's move to Section 3, the Solstice Node Space Relay, and see how this builds. Now, you might be wondering, why go through the trouble of sending the signal to space in the first place? Well, it's because the atmospheric boundary layer is an absolute threat to our fragile little package. It's incredibly chaotic, full of scattering risks, and totally opens the door for side-channel eavesdropping. But the vacuum of space? It is the perfect safe haven. Out there in low Earth orbit, there are 0 air molecules, 0 moisture, and absolutely no dust particles to scatter the light or cause decoherence. So by pushing the signal up into space, we basically bypass the messy, dangerous conditions of Earth entirely. Once we actually hit that safe haven of space, we reach step 4, satellite ingestion. Basically, a Solstice node satellite in low Earth orbit intercepts that targeted V-band uplink. But our photon doesn't just hang out there. In step 5, the true magic happens: constellation cross-linking. The receiving Solstice node routes the data horizontally right through the satellite constellation. It passes the packet from satellite to satellite using these ultra-secure, vacuum-isolated laser crosslinks. It's zipping through thousands of miles of empty, safe vacuum until it's hovering directly over its final target on the exact opposite side of the world. No way for anyone to intercept it. Which brings us to our descent. Section 4, landing at Jitterbug Hub B. Okay, so returning back to Earth requires immense precision. In step 6, the final Solstice node in that orbital chain beams the V-band signal back down through the atmosphere. Down on the ground, Jitterbug Hub B is waiting for it. It intercepts the beam using highly targeted tracking arrays, safely pulling the photons back down into a localized, shielded environment. And then we hit step 7, the localized frequency phase match. The incoming photons enter the destination hub's own MIG-ZN and Ruby crystal matrix. But here's the catch. The environment at Hub B is naturally going to be slightly different from Hub A. To solve this, the receiving hub runs a specific frequency phase match algorithm. Because the system has calculated the exact environmental offsets, this algorithm takes that incoming wave packet and matches its phase perfectly with the local environment. It's almost like taking a delicate instrument out of its case and instantly tuning it to the exact temperature and humidity of the new room.
And finally, Section 5, Perfect Quantum Reconstruction.
The photon's global journey is complete, and the payoff is absolutely massive. So the crucial point is this quote right here. The quantum state is cleanly reconstructed on the other side of the world, achieving absolute systemic clarity with zero intermediate exposure. Just think about what we just walked through. From the perfectly stabilized maglev deck at Hub A, shooting up through a precise V-band uplink, zipping horizontally across thousands of miles of ultra-secure space vacuum lasers, and then back down through that phase-matching algorithm at Hub B. Our fragile package was never scattered. The result? The ultimate unhackable payoff. Zero intermediate exposure.
We've detailed the physical routing mechanics of this incredible architecture today, but it really leaves us with a fascinating, provocative question to ponder. The math behind predicting those environmental offsets and the constellation passing is just entirely next level. So what specific algorithm parameters does the 5A matrix actually use to calculate these massive orbital handoffs? We're going to explore exactly that in our next module. Keep learning, and I'll catch you in the next explainer.